Good morning. Happy Friday. We made it to day 23. That gives us 23 and 45. Three puzzles left. Three puzzles left. With the advent of code here. This is my first advent of code. It's been fun. Been enjoying it. There's only been like maybe 2 days where it's oh geez, did not want to be here. Smab. Good morning, my friend. Or good afternoon for you, I suppose. It's nice to see you. Nice to see you. Hope you've been well. Hope you've been getting rest. Hope you are having a beautiful day. Yeah, oh, this isn't the right. Yesterday's puzzle was cool. Yesterday's puzzle was really fun. Made me want to try and write a generalized cube loader. So my solution yesterday involved, all right, so every face, so I have a face of the cube, and then there's like a known rotation from a face. If you go off the edge, northeast, southwest, there's another face, and then there's like a known rotation. How do we rotate to get there? So everything always stays sort of oriented in the way of the puzzle input, and then when you go over the edge, you just apply this rotation and then add yourself to that face. So pretty straightforward if you can, to do that. It's the loading it in that's tricky. And so I hard code my rotations, but So I load each chunk of board, a 50 by 50 board. You could generalize this to like have the size of your faces, your cube faces, and then load them up. And then based on the way it's folded, do a rotation. So I think it would be pretty cool to write a generalized version. This works specifically for the 50 by 50 input in the specific configuration, but it'd be pretty cool to do it. Let's take a look at your solution. You always have great solutions, by the way. But I thought that was such a fun puzzle. Let's see here. Monkey map. Test cube topology. Int to point. I'm gonna assume that I don't need to. Oh, this is the test cubes but topology. This is your cubes topology. Gotcha. Yeah, I labeled my faces this way too. 1, 2, 3, 4, 5, 6. My labels were the cube in the top right corner was my 1. So I had like a die and then I like sort of rolled it across to understand how it would do it. Yeah. Oh, this is interesting. Int face facing. I'll go down to the bottom, see your diagram. Gotcha. Yeah, I have something similar drawn out on oh, did my Remarkable install an update here? Yeah, I might not be able to use it right away. Gotcha. Yeah, the topology was really interesting. I did manage to figure mine out, but couldn't trust my brain, so I ended up cutting out a cube to verify how all my corners matched up. I don't know where my cube went. Now I'm sad. Must have. Oh, here it is on the ground. Yeah, I made myself a little cube to understand how the corners match up so that I could understand the rotation. I come here. We have, where's my button here? Document cam. So I have oh, come on. I believe in you, camera. Focus. There it is. So that's something similar. So my idea was that when it's out flat like this, all of the corners go clockwise A, B, C, D. And I had written down how they all relate to each other initially and was pretty confident of it, but like I couldn't quite wrap my brain around it. It took me 20 minutes to figure out how to cut out, to get a piece of paper. I couldn't find scissors, so I ended up using like a box cutter. But yeah, folding it up to understand, each side when it comes to it, how do you need to rotate? So I think it'd be really cool. So given when you're in this position, if you go off the right edge, we have to rotate twice, 90 degrees twice. Really, really fun puzzle. Not tedious, right? Well, I mean, I guess there's some level of tedium to it, but not tedious from a programming perspective. Just a really cool, like, you had to really think deeply about what was going on here. I would love to, probably never will, but I think it'd be really cool to try and figure out a generalized one where you could like analyze a picture, determine, given the top left corner of every face in your cube, it like sort of will automatically fold it into a cube or tell you it can't be folded into a cube. I think that would be really interesting. Or I mean, hard coding all the different possible cube foldings I think would be a nightmare. It'd be really cool But once I had the rotation, I just used all my code from the original one aside from the wrap. So my cube solver. Oh, and then translating back to global position. Had a little visualizer even. The visualization was pretty cool. Yeah, so I ended up writing a little visualizer that I thought was fun. I had one little rotation bug initially. Mine breaks it up into 6 arrays. All right, so let me zoom out here. Oh, I'm gonna zoom out one more. I don't know how it's come. Really? There we go. I guess it's really hard to see here, or might be. I'm not sure if you can tell, but this is saying which face we're on. It shows it draws it on there and then tells us what we're gonna do. All right, we're gonna rotate left. And then this helped me validate, okay, I'm about to go from face 1. If I walk off the edge, I should be on face 2. And now I'm down here. Just for being able to draw it onto the screen, it was super useful. So yeah, going off to face 3, I ended up here. So it's kind of cool to hold my cube out and look at it. This worked out really nicely. And this quote-unquote visualization wasn't hard to like really write. But it was pretty fun. And I was going, oh, this would be so cool to map onto like an actual cube and then do it. And other people did this. I saw all sorts of cool visualizations. But I really enjoyed this puzzle. It was really fun. Programmatically not terrible. Not even real. I wouldn't even call this programmatically difficult. It was, the puzzle was thinking in 3D. Thinking in 3D. I was reminded of Star Trek 2. I watched Wrath of Khan, Star Trek 2, 3 or 4 days ago, and I just, the part was going like thinking in, gotta think, they outsmart Khan because they think in 3 dimensions. Khan thinks in 2 dimensions. So I felt my brain couldn't wrap around the 3 dimension. We're gonna do day 23 here now. New. I enjoyed writing it too. So it was a nice little, and luckily I didn't have any real bugs. I didn't have any real bugs. My code could use a refactor. But my code's not terrible. I don't think my code's terrible, but it's not the best code. There's actually a bunch of little things in there that I ended up not using. Yeah, yours is a bit different. Mine thinks of it in an actual cube. Yours has the direct mapping for each side. Says, okay, well, if I go here, I go off. So you have like the translation of each of your faces, right? So in mine, when I do the actual solve here, one sec. I have this sort of, where is it? Next position in my face. All right, so every face of the cube is aware of the neighboring face. So if I go off the north side, what face do I go to and what rotation do I apply? If I'm on the board, so if I'm inbound, so when I go to step, if I'm on this same board, if I'm still on this face, just check if it's open. If it's not, stay in my same spot. Otherwise, move to an open space, and then throw a little thing here. And then really, we just say, okay, given our facing and rotation, find the face I want to go to, and then wrap around. So make sure I stay within 0 to 49 for my rows and columns. Rotate clockwise the number of things. So this allows me to rotate. So the position I was at, I move off and it sort of wraps me back. So, oh, well, I need to be on this edge. And then I rotate to my correct location on that edge. So it rotates around. And then same with my face, and I just rotate my face. If I'm a wall, I don't go. So I rotate my position, check if it's a wall, and then I update like that. Like I said, the parsing isn't even that bad. It's I've hard coded how each face interacts with its neighboring faces. This would be really cool to generalize, I think. I think this would be a really fun spatial problem to generalize of how do we fold a cube, or even two planes that are next to each other. If you have a fold, how does it interact with it? That would be, I think, really interesting. I think it'd be probably really hard to think about. But yeah, if you only did 90-degree folds, shapes, you know, all these geometric shapes that aren't necessarily circular, right? Or sorry, it's squares. So like, what if you had a box, rectangle? How would it fold? Or even, you know, someone posted all the ways on Reddit. I think there's like 23. It was way more than I thought. So, or 12. It was quite a few. Someone posted a really interesting idea for part 3. Imagine you have a cube, but the top is open. Right? So you have a top. So if you go off the edge of a face, it actually wraps around to the like inverted, so it's flipped, and then you can actually go inside the cube and traverse around. So it's, instead of being a cube, the top is open, and if you go off the edge, you actually wrap around inside. And I was going, that was really cool. So a box or a shape that some of the sides connect, but not necessarily all of them. I thought that was a really cool part 3. And my solution actually would work. Again, all I got to do is hook it up here. It says, so if I go off the north side of face 1, I actually end up on face 1 rotated 20 or 180 degrees. So mine would be a mild modification to actually do it. I just gotta redefine all my faces. Really cool puzzle. All right, let's take a look at what today is. I think I looked at the title. I haven't read the puzzle though. Folding was a puzzle last year. Yeah, it makes me just, an origami puzzle would be really neat. With square grids, you're sort of limited in certain, I hate when it does that. Nah. There we go. Okay. All right, let's have a look here. Yeah, our solutions are we took pretty different approaches, I actually think. I like your solution feels a lot feels clean, feels very clean. This is the same type of mapping I did though. I just implemented a rotation for like a rotating on a square. Sweet. All right. Unstable diffusion, day 23. You enter a large crater of gray dirt where the grove is supposed to be. All around you, plants you imagine were expected to be full of fruit are instead withered and broken. A large group of elves has formed in the middle of the grove. But this volcano has been dormant for months. Without ash, the fruit can't grow. You look up to see a massive, snow-capped mountain towering above you. It's not like there are other active volcanoes here. We've looked everywhere. But our scanners show active magma flows. Clearly, it's going somewhere. They finally notice you at the edge of the grove. Your pack almost overflowing from the random star fruit you've been collecting. Behind you, elephants and monkeys explore the grove looking concerned. Then, the elves recognize the ash cloud slowly spreading above the recent detour. Did you just? Before any of them can form a complete question, another elf speaks up. Okay, new plan. We have almost enough fruit already, and ash from the plume should spread here eventually. If we quickly plant new seedlings now, we can still make it to the extraction point. Spread out. The elves reach into their pack and pull out a tiny plant. The plants rely on important nutrients from the ash. They can't be planted too close together. There isn't enough time to let the elves figure out where to plant the seedlings themselves. So you can quickly scan the grove and note their positions. For example, scan shows elves and empty ground. Outside your scan, more empty ground extends a long way in every direction, so we got an infinite grid. The scan is oriented such that north is up. Orthogonal directions are written north, south, west, east, north, south, west, east. No, okay, so then we have diagonals as well. The elves follow a time-consuming process to figure out where they should each go. You can speed up this process considerably. The process consists of some number of rounds during which elves alternate between considering their move and action. Cool, we're going to do a cellular automaton. During the first half of each round, each elf considers the 8 positions adjacent to themselves. If no other elves are in one of those 8 positions, the elf does nothing. The elf does not do anything during this round. Otherwise, the elf looks in each of 4 directions in the following order and proposes moves 1 step in the first valid direction. All right, so if there's no one near them, they don't do anything. If so we're trying to spread out, so you have no one in the 8 adjacent positions. Proposes to move 1 step in the first valid direction. If there is no elf in the north, northeast, northwest, the elf proposes moving north. Okay, so they're only going to propose moving north, south, west, east. So we can only move orthogonally. We move north if there's no elf to the north, any of their north positions. South, no one to the south of us. West, if there's no one to the west of us. And east, no one to the east of us. Okay. After each elf has had a chance to propose a move, the second half of the round can begin. Simultaneously, each elf moves to their proposed position if they were the only elf to propose moving to that position. If 2 or more elves propose the same position, nothing happens. Finally, at the end of the round, the first direction the elves consider is moved to the end of the list of directions. Hang on. Finally, at the end of the first direction the elves considered is moved to the end of the list of directions. For example, during the second round, the elves would try proposing a move to the south first, then so they use this order in the first round, and then this sort of goes to the end of the options, and then they'll start with south. So we just sort of have this round robin approach of selecting. Okay. It's a small example. The northern 2 elves and the southern 2 elves all propose moving because they're adjacent to someone. The middle elves cannot move north and proposes moving south. The middle elf proposes the same direction as the southwest elf, so neither of them move, but the other 3 do. Okay. Next, the northern 2 elves and the southernmost elf all propose moving. All propose moving south. Gotcha. Moving south. This is because they choose south first rather than going north. Okay, interesting. Finally, the southernmost 2 elves choose not to move at all. Of the remaining 3 elves, the west one proposes moving west. The east one proposes moving east. And the middle one proposes moving north. At this point, no elves need to move, and so the process ends. All right. All right, then we just have a big, not necessarily a big test, but it tests some tests we can look at. To make sure they're on the right track, the elves like to check after round 10 that they're making good progress toward covering enough ground. To do this, count the number of empty ground tiles contained by the smallest rectangle that contains every elf. The edges of the rectangle should be aligned. Okay, so we find the bounds northeast, southwest. Calculate the size. Oh, my Remarkable just died. That's sad. I'm gonna plug it in and I don't know where my plug is. And then else not. How many empty ground tiles is the rectangle type? So then it's, you know, the size of the rectangle minus the number of elves in it. Okay, so we're gonna simulate 10 rounds of this. Got to build up our rules. Cellular Automata. I typically like this type of puzzle. We'll see if I get frustrated. So we have an elf on the grid. So public record elf. And an elf has a position. Key. New file position, public record position, row, int column. Transparent origami. I say I'm gonna check it out, and I might. I would like to check it out, but we'll see if my brain can remember. So our elf will have a position. I don't even know if I need to have an elf type. I really just need a position type. Yeah, this will just be a... Well, let's look at my input. My input look like. All right, it's just the grid. Not even that giant of a grid. All right, so we have our example. Input. I'm just gonna call this grid. I'm imagining the second point is simulate until it stops, the second puzzle, but I don't want to jump to any conclusions yet. So we have a grid, and our grid is gonna have a set of hash set of position occupied. So it's just gonna have all the elves that are occupying it. And then we simulate a step to get the next. Well, we do two things. We have to check there's no elf, so we have sort of this idea of direction. All right, so position, public position. Now let's add a toString to this. I'm about to do a recursive thing. Public override string toString. And this will return position row column like that. And we'll get our neighbors. So public position north, keep it simple, and this is this with row -1 column. All right, let's see how they do they define. I don't think they even care about XY positions. Yeah. We just have to find the grid, like where this positions are, the size of our rectangle at the end of the day. All right, so I don't think we care about public position northeast. This with column equals column +1. We got a south. We've got a west. And then we have public position northeast. Row equals north dot row. Column equals east dot column. Is this dumb? This is super dumb, right? Northeast, north, west. This is dumb, but I'm going with it anyway. South. All right. All right, so we have our directions. And we have some rules here. The rule. All right, so we will have public record rule is going to accept a set of positions, so position target and position param. Can I do params? Position to check. I always forget, is it position params? Or I might not be allowed to do it here. That would be params must be a single. Oh, do I have to do? There we go. All right, params to check. And then our rule, public bool can move this isn't quite right. So we have to I really wanted this to be nice. Hang on. I can do this. I can make it work. This is public. Really want to make it work. Really, this needs to be a function from position to position. Which well, we'll see. To check. So we can move. And this will become a function position. Over complement rule. Yeah, so given a position from and a hash set of position occupied. And we'll return true if we can move into that position. Yeah, so then we will say for each position P in from in this is the var we need to apply each one of these, so it's actually a var func position options, or look to check in to check. We do check dot invoke on from position P, and we just say if occupied dot contains P. Yeah, here we go. This is going to be simplified greatly. Rewrite this as a link here in a second. Then we will return false. And if we get through all of them, return true. Okay, so really we are doing to check dot select f goes to f dot invoke from dot where occupied dot contains dot any. So any will return, or we want it to be none dot empty. We'll do dot any and then not that. All right, I think that does it for us. Func is just saying I'm going to pass in a lambda expression, or a what would this be? This would be an anonymous function, and then invoke is just call that function. So yeah, then we have our grid has a queue of rules. So public, and the queue sort of like at the end of the day is going to move its thing from pop it off the beginning, move it to the end. Queue rule, and so our rules become yeah, so our target, we do need one more thing here that is our target. So we need one more function, position target. So this will move us to that position. All right. So let me make each of our rules real quick. Public rule, public static rule, move north is equal to a new rule. And the rule would be a function, so P goes to P dot north. So, all right, and then the things we're checking is P goes to P dot north, P goes to P dot northeast, P goes to P dot northwest. All right, so our rule says move to this position if none of these positions are occupied. Move, so we do north, south, yeah. Move south. Honestly, these should be part of rule. These are like constants. Public, static, read only. And we move south if south, southeast, southwest. North, southwest, east. Move west. Move west if west. Northwest and northeast are empty. And we move east. If any of those are empty. All right, so we have this nice little rule that tells us whether or not we can move. So we have a can move, and then, you know, target is a terrible name, but I can't think of a better one because I'm just not great. So step one becomes public hash set position movers. So we're gonna get all of our movers here first. This should probably just be called solver. Movers. I kind of need to be able to change it. So public. I'm not gonna worry about it real quick. So, but hash set movers. We. Oh, I need my rules first. So, public queue of rules get private set, and initially, well, this queue thing has trouble, but it's gonna be an array here. Move north. Gee, happy Friday, my friend. No worries. You're never obligated to be here. I love when you're here though. I love having you. My brain here. Trying to think. Why can't my brain handle this real quick? I want to get a queue of rules here. Public static list of rule. Oh, this is annoying. All right. Here's how we do it. Private queue of rules equals new. So we get one there. Actually, we don't, but that's fine. Private set is rules equals value. The first time we do a get, here we go. All right. So the first time we do a get, so it'll be null initially. And we just say if rules is null, rules equals new. Then we add each of the things to it, and then we return rules. There we go. I was struggling. I got it though. This feels like too much. But Q has issues with, there's not like a link.toQ thing. And so we'll do rules dot add append in queue move north. Just NQ each of these. So we have move north, move south. The order is north, south, west, east. Move west, move east. All right. And after each round, we take the first thing and move it to the end. Q is probably not the right way to do it, but it's fine. No, it's not 2. There's no 2Q yet. So movers. We're gonna find all our movers. So we start with the hash set position. Movers equals new. I'm gonna return movers at the end. And we just build this up. We say for each position and occupied. So position elf in occupied. And then for each rule in rules, we're gonna say r dot can move. Our from position is our elf, and our occupied is here. So if we can move movers dot add elf. All right, so we're gonna put all these in here, and then essentially we need to update our queue here. So I'm not sure if I really want to have that as part of movers, but that's fine. We'll put it in here for now. So rules dot dq. We're gonna get the first thing here. So rules dot inq, rules dot dq. So this sort of moves first thing to the end. So we got movers. And we need to actually perform the move. So we don't want to do this yet. We don't want to do this yet. We want to do this. So find, so we're going to find movers. Public hash set position. And then we need to actually have a move. Move hash set position. So now we need to sort of see, okay, well, what positions? Oh, this is a little trickier than initially thought. Movers. Because these positions will need to get. This is going to be the thing. These are the people that actually move. These are the elves that actually moved. And so this is going to be like new positions, but we actually need a list of like the positions to remove as well. So at the end of this, I'm going to turn to add, and then also a hash set to remove. So if we actually moved, we got to remove it from our hash set. Yeah, so we get back two things here. Oh, I guess I could just get back a hash set of all the positions that are actually going to move. All right, that's what I'll do here. And then I'll have one last tip. G, you're on, I think I'm right. You're on, like break? You're in school, is that correct? You're at university and you're on break now? All right, so we're gonna start with a hash set. So if two elves are trying to move to the same position, I gotta think about this position. Movers. Can't call it movers. New occupied. So So it's gonna be like when we see someone, they move into this, and then we sort of like Smab, man. You know, it seems like you're always running on fumes. Running on fumes. I went to bed early last night. When I was asleep by 9 o'clock last night, I think. Maybe even a little earlier. New occupied. Actual movers. Target positions. So we need to say if by applying so this is going to be we can move if no one else moves into that position. So for each position elf in movers, we already know that the space that they're attempting, there's like potential for them to move in there. Oh, we just have to have a count. We have to count how many elves are in each of those. All right. So we're gonna use a dictionary here. Dictionary position, int. All right, so you know, target. All right, so we use a dictionary, keep track of how many elves have tried to move into that spot, and we keep all the ones that are equal to 1. Yeah. For each. Does anyone know? Is there a dictionary type that's like with default, so that you always have like a null, like it assumes that there's a 0 there? For each position elf in movers. We could do this all in one here. That's okay. So we're gonna do it again for our rule here. Really, I should be doing it here, but I've already put myself here. I'm gonna keep going here. We already know that they can move. So now we're just checking. Yeah. So now we do. Oops. R dot. What happened here? That was interesting. So we know that at this point they can move, and so it's gonna be R dot target dot invoke L. So this will be their new position. Position new P, and we say if target positions dot contains key new P. It doesn't contain it. Target positions of new P equals 1. Else, this means it contained it. Target positions of new P. Can I do ++ here? Hey. I'm slightly worried that that doesn't work. All right, so then down here at the end, we say, all right, well, we only keep, so target positions dot, Dota, hey, happy Friday, my friend. How we doing this morning? So we got a key value pair. Christmas break has started. Well, welcome to Christmas break. I hope you're enjoying yourself. Oh, what type of programming language are you thinking about doing? Um, so we only keep it, and then we select key value pair goes to whatever crafting interpreter that implements. I haven't used that one. I have my favorite one is build you a scheme in 24 hours or something like that. To hash set. It's in Haskell though, so I think you have to want to write Haskell code at that point. But yeah, build you a scheme. Returns void. Ooh, writing interpreter. This should be a hash set of position. Return P. Oh, here we go. I named my variable there. Gotcha. That sounds fun. I love, in the past, when I was in grad school, I was really into programming language design. So I've written, never anything serious. The most serious I've done is working on the Elm compiler. But I think compilers and interpreters are really, really fun. You learn so much implementing them. So, you know, implementing an object-oriented programming language, implementing an interpreter for an object-oriented programming language is really, really fun. You learn a lot about how things interact with each other, the memory model. So we actually get the moves. Find moves. So this should probably be combined into a single thing here. Really, we do this up here. So we say if we can move, do this. And then at the end of the day, this isn't quite right, actually. I'm gonna go back here because I'm realizing this isn't quite right. This is my target positions. But I need my the position that I'm moving from as well. Yeah, so this is the position we're moving to. So I'm going to change this actually to be a list of positions that we're moving from. So really this will be a new list with elf in it. Yeah. Dot add. And then right here, if our, yeah. This is gonna be dot count greater than 1 equals 1. Yeah, Cellular Automata is so cool. If you haven't done it before, Langton's loops. Langton has all kinds of cool stuff. Langton's loop is my favorite one. Not my favorite, but my favorite simple one. I like to use it. So what you will do together, we'll do Game of Life usually, and then I'll be like, okay, now implement Langton's ant. All right, and then Langton's loops. Langton's loop is like a nine-state cellular automaton, which I think is really cool. This needs to be position to position. Yeah. I didn't hard code a kind of topologist, I implemented mine with multiple faces. So the left side should be key value pair dot value of 0 goes to this position. There we go. And then I hard-coded the particular topology with the rotation, saying when I go off, if I'm on face 1 and I go off the west side, I need to do a specific rotation number, like clockwise rotation. I really enjoyed it. I thought it was fun. The coding for me was not tedious. I thought the problem was a really interesting, cerebral is what I would call it. It was a cerebral problem. I really had to think about it, and that was fun. All right, so if you stick around a little while, if I finish this, I'll talk about it a little bit. I'll show you what it was. But yeah. Yeah, I was lucky. I had like one little bug, but I built a little visualizer for myself that was pretty straightforward. That made it really easy for me to debug. I had one rotation problem where I was rotating counterclockwise instead of clockwise. My brain, I thought I needed to go counterclockwise, but it turns out it didn't. All right, so a single step here. So public grid step. Okay. In a single step, I need to first find potential movers. And then I need to find a hash set, position, moves. Find move, potential movers. And then I create a new hash set that we'll copy everything from this real quick. Occupied, new occupied equals occupied dot to hash set. So that should clone it. I didn't even do the sample input, if I'm being completely honest. I didn't do the sample input. It felt, so I looked at mine and I looked at the example. I goes, oh, well, this is, yeah, I didn't even use the sample input. I just went for it. I knew the folds weren't the same, so it wasn't gonna, like, yeah. It was gonna be, yeah, anyway. New occupied. All right, so then we say for each position from position 2 in new in moves, we need to remove new occupied dot remove from new occupied dot add 2. And then our queue rotates. So then we'll create a new rules queue. I guess this will just update our actual grid. So update our actual grid. So I don't even need really do new occupied. You're a topologist, clearly. So this doesn't actually do this here. Instead, we just update our hash set there. We remove those, we add those, and then our queue rules.inQueue rules.dq. So after we're done, rotate rules. Okay, so I think our general plan's in place. The question is it going to actually work? Let's write a toString here, public override string, toString. It seemed ideal given your name. You guys are hilarious. String builder B. We are gonna loop through. Oh, we gotta find our minimum and maximum here. All right, so we have public position top left is going to be a get here. So we're gonna do for each position top left is equal to new position int.max. My rows decrease going down, yeah, int.max. And then we'll say for each position p in occupied. At the end of this, return top left. For each position p in occupied, if p dot column or top left equals new position with math.min of top left dot row comma p dot row and math.min top left dot column p dot column. So we find our minimum there. Probably do this better with link, but I'm gonna just not for now. Get our top left, get our bottom right, bot right. Hang on, bot right. Sure, there's gonna be a copy paste bug here. I probably shouldn't do it this way. Min value here, loop for position. This time we're looking for the max. All right, so this will get us our rectangle, and then we can loop through saying for int r equals top left dot row, r is less than or equal to top bottom right dot row r plus plus, for int c equals top left dot column less than or equal to bottom right dot column c plus plus, b dot append. Now we gotta check here if occupied dot contains new position row column b dot append hash, else b dot append dot b dot toString, and each row we want to append a new line, and then we're going to trim the last new line off. Okay. Oh, I haven't written a parser yet. I got to parse my data in. Okay. I always end up with so much code. I look at, SMAB. I'm always impressed at how concise your code is. Keith wrote really concise code too. My code always feels massive. I guess it's because I'm not using link as much as I could. Yeah. I'm not using link. If I was using link, this would be more concise. These curly braces make everything feel giant. When I go back and I look at it, it doesn't look complex. My solutions are rarely Very complex. All right, I gotta write a parse. Who needs to just imagine the result? Public static grid parse string rows. Position occupied. Yeah, the little micro solutions always. I'm always fascinated. This should be called solver. I hate that I'm calling it grid, but that's okay. For each, need rows and columns, so I actually have to do for int row is equal to 0 row less than rows dot length r plus plus. For int c equals 0, c is less than rows of r dot length c plus plus. Occupied if rows at r of c is equal to hash occupied dot add new position at RC. All right, let's give it a little swizzle. See if this makes any sense. String rows is equal to file.read all lines of our example.txt. A blank line at the end, there is not. Okay. And then we're going to say grid equals grid.parse rows. Console.writeLine grid do while true. I want to do it 10 times int, but we're gonna have console.readline. Add a little step here just to no test, just an eyeball test. Console and then we do grid.step, little eyeball test to see how we stack up against the puzzle. Here, little eyeball test. Uh-oh. Eyeball test fails. We're not removing positions properly. Okay. So let's come back over here and figure out why. Looks crowded. I'm not removing. This is interesting. I didn't remove. What is? I must not be adding in the remove. The movers positions. For some reason, I am let's take a look at console.writeLine from goes to 2. Let's use the even smaller example that they give. So that we can reason about it a little bit more. Create a new file, tiny. Tiny. Oh, it's not clear. Position 1, 2. Oh, well, clearly. Oh, I know what's going on. I know what's going on. I don't stop when I find, oh, I know what's going on. My movers here, this should be position and then the function that they're gonna do. Like that. So if we do that, elf, and then r dot target, and then this is a func. In generic, I need a. Oh God. All right, so finding my movers. We check them all, but then there's a specific move we have to make. This should be a list. And then this is going to continue. As soon as we find one, we need to continue. We need to break out of this loop. So if we find one, we break. For some reason I'm having write issues. We add that elf in, and it's position, and then this becomes a function from position. So this is the move we need to apply. So remember when I said my solutions are usually simple? Well, I lied. r.target. Okay. And this now becomes a list to this. And we say for each elf into target. Honestly, all right, so this is position. This should be from position to position. Sorry about the lameness here. Target.invoke elf. These are to and from positions. This makes a lot of sense. Position to position. And for each from to we don't need this loop anymore. I was basically applying all the rules to all the elves that could move, which was the wrong thing to do. So we say if it contains the to position, we say, well, that to position comes from the from. Otherwise, we add it in here. All right. All right. So I think this is a list of to and from, or from and to. From to. Is that the same thing here? From and to. Yeah. All right. I think this is closer. All right, that looks correct. That looks correct. That looks correct, and then I do nothing. It's interesting. They are still, there should be no moves. But they're sort of moving. They're moving up. They're sort of shimming around still, which I don't understand. Oh, I don't have the rule that says if there's no one next to them, they do nothing. All right, so I'm missing that rule. So there's one rule here that we always need to check first. So find movers. So if no one's near them, they definitely shouldn't move. Yeah, Smab, you're winking at me. You got it. You got this. Wow, I could have gone down a rabbit hole for a long time here. All right, so we actually say if I need a function that says no neighbors, right? If elf yeah. So in our position here, public position array neighbors is equal to a new array north, east, south, west. Oh, come on. Autocomplete east, south, west, northeast, northwest, southwest, southeast. Okay. So we're gonna say occupied or elf.neighbors dot where occupied dot contains dot any. So this will say if any of my neighbors are in there. So I say if this is not the case, continue. If the elf has no neighbors, don't do anything. All right, let's try this again. This is where unit tests are the way to go, man. There we go. Now they stop. Let's we need to go 10 times for less than 10 I plus plus. Go 10 times. And then we need to calculate the number of empty squares, right? How many empty ground tiles does the rectangle contain? So real quick, let's add that in here. Public int empty tiles, we are going to get the size. So int width is bottom col minus top left column. Is there an off by one here? Someone tell me, is there an off by one here if I'm doing it this way? Height equals bottom, or yeah, bottom right dot row minus top left dot row. And so it's should be width times height minus occupied dot count. I'm off by one. I need to do a +1 or a -1. Yeah, because it won't count the cell that it's in. So if I have 0, say my grid was size 1, I need to make sure I count that 1. All right. Console. And find the smallest rectangle that contains the elves after 10 rounds. How many empty ground tiles? Console.WriteLine grid.empty tiles. Let's try this. 1, 2, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, that looks correct. You need to print the most left and the most right one. I don't understand exactly what you're saying there, G. But let's go with our example. We'll go 10 rounds. Nothing important. Gotcha. 27. Let's go 10 rounds. I'm off by something. All right, so something went wrong here. And that's disappointing. Let's see if we can find it right away. Me trying to be clever is never the right answer here. Dot. Well, my movement I think is actually wrong, not an off by one. I think there's a rule that's not being applied well. Oh, you think my picture is actually okay? My picture looked wrong after 10 rounds. Yeah, my picture's wrong. Oh, did I just not copy the... example? No, I think that's okay. I have a bug in my logic somewhere. Oops. My other lines are off. My state here is okay. That one seems okay too. That one looked like maybe something went wrong. No, that one's still okay. Oh, the right number. Oh gosh. I'm gonna end up the example. It's correct through there, and then something goes wrong. Oh man. Feel like, all right. Let me print out the number of occupied tiles. The small example, the small example works. Yeah, the tiny example's fine. I just have some rule that I'm doing wrong. Yeah, the tiny example works fine. Hang on, let's go look at my north, east, southwest, northeast, northwest, southwest, southeast. These look okay. My rules. North, northeast, northwest, southeast, southwest. At a glance, these look okay. All right, I was gonna print out, see if I'm losing any elves somewhere along the way. Console.writeLine grid.occupied.count. Oh. Should have written tests every time. Let's go to my example here. It sort of looked like some of the elves were getting deleted or something. 22. No. Oh. Okay. Well, it shouldn't matter. It shouldn't matter. I'm doing 10 steps. It shouldn't matter. I end up getting off here. Console.writeLine I. You're right. Maybe one step is missing. Oh my god! You were right. Why to make sure the elves, let's check after 10 rounds. Oh, after 10 rounds. Okay. Topologist. Thank you. I was about to spend the next 30 minutes killing myself. Yeah. And I wasn't actually, I need to do this last step and then do it one more time at the very end. So after the 10th step, yeah. Off by 1 round. Woo! All right. Jeez. Yeah, so I'm printing before the round. So thank you, Topologist. We're gonna comment this out. And this is our solution for part 1, I hope. Let's get out our console here. Okay, and then let's get our input. Whew. That was a close, almost sad day for me here. I gotta actually change my program to use the input. And hope for the best. All right. Topologist, you saved me from myself. Part 2. It seems you're on the right track. Finish simulating the process and figure out where the elves need to go. How many rounds did you save them? The example above, the first round where no elves moved was 20 rounds. And the example of the first round where no elf moved was round 20. Figure out where elves need to go. What is the number of the first round where no elves need to move? Okay. So I think this is pretty easy to do. I return a bool saying true if we had movers. If potential movers dot count is 0, return false. Otherwise we do this whole thing and we return true. Ooh, it's not potential movers. It's what is the number of the first round where no elves actually move? I think this should suffice. But you could end up with collisions. So it's actually when moves is empty. You could end up in a weird state where none of the... Maybe. Well, we'll see. All right, so then let's write another off by 1 error. I'm sure I'm going to do another off by 1 here. That's my, it's just how I roll. All right, we'll go back to the example real quick. Void part 2. Part 2. We'll get this in here and we'll say while int rounds equals 0 for I like this, rounds equals 0, rounds plus plus. Look at me being silly. Well, grid dot step. This is dumb, right? Console dot right line rounds. Rounds has to be defined before. This is a cheeky, dumb thing to do. And then I have to call part 2. Yeah, I have an off by 1. Technically, yeah, I have an off by 1, so it should be +1. Oh, I need to start my rounds at 1. That's why. Okay, let's try it with our input. Smab, I paid attention today. Oh boy. 925. Okay. Mine was short. Mine was only 925. You guys were saying yours was 4,000. Got lucky. Got lucky. Yeah, there's some optimizations I suppose you could do in this. Oh, Ron over on YouTube. Sorry if I missed you. If you're still around, I just noticed there was someone chatting with me over there. Ron, I'm working on Advent of Code Day 23 puzzles. Probably have the same input. All right, 2 stars. Under 2 hours today, which is nice, which is really nice. I love this picture. We got some ash coming up over here. I guess we're over here. This is our grove. Yeah, this is cool. I like how it unfolds here. I kind of wish I'd been taking screenshots of this every day so we could watch little animation. 2 more days, and we're done. Smab, let's check out your solution. Oh, let me commit this real quick. Git status. Make sure I'm not committing anything crazy. Yeah, git commit -m. Chore implement day 23 parts 1 and 2. I like when my part 1 solution makes part 2 very easy. I know I think this is the longest I've committed to something like this, doing it every day, so it's been pretty satisfying. Here we go. Direction order, north, south, west, east. Okay. Direction offsets. So this is like your northeast, northwest, southeast stuff, I'm assuming. Part 1 number of 10s, process round. Wow is false. Plus another 10 days for you to solve day 16. Yeah. Load elves. Process round. All right, so we have strings to point. Choice offset. Gotcha. So this is the choice offset is sort of the selection of which direction we're going to go. We're building up a list of proposed move. Gotcha. Elves.values to hash set. So we get their points. We find out which elves can move. All right, so this is something I forgot to do initially. I just said, every elf, see if you can move. So these elves here, checking if they can move. Yeah, Smab, we talked about doing Monte Carlo for day 19. I remember that. I was jealous of your solution. I racked my brain. Yeah, it totally works. It works for day 16 too, it turns out. You have to run a lot more rounds on day 16. But yeah, day 19, the path is super easy. So, yeah, day 16, your iterations have to be way bigger. And you still have to compute all pairs shortest path to make it efficient for Monte Carlo in there. Go through all of our elves, all of our points. If we can move that. This is the break I forgot initially. What for day 16, what was your approach? Did you build up a graph? Day 16, I feel like I got pretty quickly using memoized recursion. So calculate all pairs shortest path, and then memoize recursively, essentially depth first search over it, memoizing as we go. My solution was very quick on that one too, I think. Day 19, I just finding the right optimizations took forever. And then no moves, return no moves. Mab, nice solution here. I like this process round, concise, easy to read. No, nothing tricky about it. And then you've sort of implemented these things. I will say I do like the way I did my rules a little bit better than the way you've done it. I was really happy with the way I did my rules. What did I click? Because they came out pretty nice. This is a nice solution, Smad. Oh. All right, I'm gonna get, let's see, we got 17 minutes left on the stream. I'm gonna grab a cup of coffee and then maybe do something. I don't know, but I'll be right back. All right. Let's see, what do we have here? Came up with a different algorithm. Part 2 of my day 15 was ugly. Put my headphones on here. It's basically about the fact that the elephant was a completely separate entity. Oh yeah, this took me a while. That's right. On day 16, I actually implemented the wrong, for part 2, I implemented the wrong thing initially. Where I thought my initial solution, oh, let me stop that copy screen there. My initial solution for day 16, I had it so that way, I thought you could train more elephants. I thought you had like I thought you had a new choice at every step of train more elephants or go do a thing, and so my project was crazy. And then my final solution that I did wasn't the most efficient. It is another recursive dynamic programming memoization one where I have 5 states now. So I have like sort of the elephant and player's position at each step, and they sort of go off, you know, and check which one can do something. So it's recursive. It's pretty big. There's a better solution where you sort of find 2 paths for a single person. You find where they don't. Yeah, exactly. So this is the part. Although mine didn't take 26 minutes to solve. And there were like 26 within 26 minutes. Gotcha. Yeah, because you had a timer of minutes to solve an optimal path. Yeah, my part 1 was really quick. My part 2, I think, 90 seconds. Ron, have a beautiful day. Thanks for hanging out. See ya. You're always welcome back. Come back anytime. Cool. So I'm hesitant to start anything new in the 12 minutes essentially that I would normally be streaming here. I'm happy to have solved this, but I think I'm gonna actually stop here a little bit early. If anyone's interested, I'll be back on later this afternoon. Continuing to work on my Space Raiders project for my students, which has been pretty good so far. I got my enemies spawning. We're almost done with it, and then I'm going to turn it into a tutorial series. I have to add in maybe a couple different types of enemies and an overlay. So like add in a HUD, a start screen, a play screen, add some sound, and probably 1 or 2 more sessions here. I might finish it today or tomorrow, and then put together a project for my students with it as a basis. But yeah, if anyone's interested, I've been working on this, and I'll be back later today to stream that. Or if you want to go back, watch the archives, see what's going on with it. Any advice is welcome. If anyone knows anything about Unity, I'm somewhat Unity noob, a Unity noob, I would say. Yeah. Nice. 2 puzzles left. 2 puzzles to go. I'm a little worried. People have said like we haven't gotten a quote-unquote nightmare puzzle yet, but I'm not sure if that's true. Day 19, day 16. What a fun little thing. Happy it exists. All right, everybody. Thank you so much for hanging out. As always, keep coding, keep growing, and have a beautiful day. I'll see you next time.